What is the universe made of? This question has puzzled and fascinated scientists and philosophers alike for millennia. How did it all begin? The origins of the universe have been a subject of wonder and speculation since ancient times. These questions have captivated humanity for centuries, driving us to look up at the stars and seek answers in the cosmos. Physicists have long sought a single, elegant theory that could explain all the fundamental forces and particles in the universe. This quest for a unified theory has been one of the most ambitious scientific endeavors. This elusive theory of everything has driven scientific exploration, pushing the boundaries of our understanding and leading to remarkable technological advancements. In the 20th century, two groundbreaking theories revolutionized our view of the cosmos. These were quantum mechanics and general relativity. Quantum mechanics revealed the bizarre behavior of matter and energy at the smallest scales, uncovering a world where particles can exist in multiple states at once and entangle across vast distances. Meanwhile, Einstein's general relativity described gravity as the curvature of space-time caused by massive objects, providing a new understanding of how the universe's large-scale structure operates. However, these two pillars of modern physics seem incompatible, clashing in extreme environments like black holes and the very beginning of the universe. The search for a theory that can reconcile these differences continues to be one of the most profound challenges in science today. String theory, a revolutionary idea in physics, offers a potential solution to this fundamental problem. It suggests that the universe is made up of tiny, vibrating strings, much smaller than even the smallest particles we can currently observe. These strings are the fundamental building blocks of everything, like the notes on a musical scale. Imagine a guitar string. Depending on how it vibrates, it produces different musical notes. Similarly, in string theory, different vibrations of these fundamental strings give rise to the different particles and forces we observe in nature. Electrons, quarks, photons, gravitons, they all emerge as different notes played on these cosmic strings. The Standard Model of Particle Physics, a highly successful theory, describes the behavior of all known particles and forces except gravity. It has been instrumental in our understanding of the fundamental building blocks of the universe, predicting the existence of particles like the Higgs boson, which was confirmed in 2012. However, despite its success, it has limitations. It doesn't explain the existence of dark matter and dark energy, which make up the majority of the universe. These mysterious components are invisible and interact very weakly with known matter, yet they exert a significant gravitational influence on galaxies and the large-scale structure of the cosmos. Nor does it explain the mass of neutrinos or offer a complete understanding of gravity. Neutrinos are incredibly light and elusive particles that pass through ordinary matter almost undetected, and their tiny masses suggest physics beyond the Standard Model. String theory goes beyond the Standard Model, providing a framework that could potentially explain these mysteries. It proposes that the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. It incorporates gravity into the quantum world, offering a way to unify all the fundamental forces. This unification is one of the holy grails of modern physics, aiming to reconcile general relativity, which describes gravity, with quantum mechanics, which governs the other three fundamental forces. By considering the universe as composed of tiny vibrating strings, string theory offers a new perspective on the fabric of reality. These strings can vibrate at different frequencies, giving rise to the various particles and forces we observe. This elegant theory, though still unproven, holds the promise of a deeper understanding of the universe's true nature. Unlike point-like particles in traditional physics, strings in string theory are extended objects. They have a length, albeit incredibly small, on the order of the Planck length, which is about 10 to the negative 35th meters. This seemingly insignificant difference has profound implications. Just as a guitar string can vibrate in different modes, producing different harmonics, so too can the fundamental strings in string theory vibrate in different ways. These different vibrational patterns correspond to different particles and forces. The universe, then, can be viewed as a grand symphony of these vibrating strings. Section 5. The Pioneers of String Theory. The development of string theory spans several decades and involves the contributions of numerous brilliant physicists. One of the key figures is Gabriele Veneziano, who in the late 1960s, while studying the strong nuclear force, stumbled upon a mathematical formula that unexpectedly seemed to describe the behavior of strong force particles. Shortly after, Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind independently realized that Veneziano's formula could be interpreted as describing the scattering of relativistic strings. This marked the birth of string theory as a theory of strong interactions. Section 6. Dimensions beyond our perception. One of the most intriguing and mind-boggling aspects of string theory is its requirement for extra-spatial dimensions beyond the three we experience in our everyday lives. To accommodate the mathematics of string theory, physicists found that the universe must have more dimensions, curled up and hidden from our perception. Imagine a garden hose viewed from a distance. It appears as a one-dimensional object, a line. However, up close, we see that it has a second dimension, curled up in a circle. Similarly, string theory suggests that our universe may have extra dimensions curled up at incredibly small scales, too small to detect with current technology. Section 7. Unifying gravity and quantum mechanics. String theory's potential to unify gravity and quantum mechanics is one of its most compelling features. In Einstein's general relativity, gravity is described as the curvature of space-time, a smooth, continuous fabric. However, quantum mechanics dictates that at the smallest scales, energy and space-time fluctuate wildly, defying the smooth geometry of general relativity. String theory reconciles these seemingly incompatible views by suggesting that at the Planck scale, the fundamental strings smooth out the quantum fluctuations of space-time. The strings, with their extended nature, provide a bridge between the continuous world of general relativity and the discrete world of quantum mechanics. Section 8. The quest for experimental evidence. Despite its elegance and promise, string theory remains a theoretical framework. Directly testing its predictions, which often involve energies far beyond the reach of current particle accelerators, poses a significant challenge. However, physicists are exploring indirect ways to find evidence. One possibility is the detection of supersymmetric particles, partner particles predicted by string theory at the Large Hadron Collider. Another avenue is the search for cosmic strings, hypothetical remnants of the early universe predicted by some string theory models, which could leave observable imprints on the cosmic microwave background radiation. Section 9. String theory and the Big Bang. String theory also has profound implications for our understanding of the universe's origin. The Big Bang theory, the prevailing model of cosmology, describes the universe's expansion from an extremely hot, dense state. However, it doesn't explain what caused the Big Bang or what existed before it. Some string theory models suggest that the Big Bang was not the beginning of time but rather a cosmic transition, perhaps a collision of brane, higher dimensional objects in string theory. These models offer a glimpse into a pre-Big Bang era and provide alternative explanations for the universe's initial conditions. Section 10. A paradigm shift in cosmology. If confirmed, string theory would represent a paradigm shift in our understanding of the cosmos, as profound as the Copernican revolution or the discovery of quantum mechanics. It would reshape our understanding of the fundamental nature of reality, from the smallest particles to the largest structures in the universe. String theory suggests that the universe is far more interconnected and stranger than we ever imagined. It points to a deeper level of reality, where the fundamental constituents of nature are not point-like particles but rather tiny vibrating strings, dancing in a symphony of unimaginable complexity. Section 11. The future of string theory. String theory is still under development, with many open questions and challenges remaining. It is a theoretical framework that attempts to reconcile quantum mechanics and general relativity, two pillars of modern physics that currently do not fully align. This ambitious goal has led to intense research and debate within the scientific community. However, its potential to unify the laws of physics, explain the universe's origin, and offer a deeper understanding of reality has captivated the imaginations of physicists worldwide. The idea that tiny vibrating strings could be the fundamental building blocks of all matter and forces is both revolutionary and tantalizing. As we continue to explore the cosmos and probe the limits of our understanding, string theory stands as a beacon of hope, guiding us towards a more complete and elegant description of the universe and our place within it. The theory's implications extend beyond physics, potentially influencing our understanding of space, time, and even the nature of consciousness. The journey to unravel the mysteries of string theory is just beginning, and the discoveries that await us may revolutionize our view of the cosmos and our place within it. As researchers delve deeper into this intricate theory, they may uncover insights that not only answer age-old questions but also pose new ones, driving the quest for knowledge ever forward.